So let's move on to our next renewable source of energy, and this is wind energy. Harnessing wind power is actually a fairly old practice. As you can see here from the ship, people have been using wind energy for quite some time. Currently, this accounts for about 2.5% of energy production, and it's based on a very basic form of energy, kinetic energy. So this will be important in this chapter. Kinetic energy, as you remember, an object in motion has energy. We call this kinetic energy, and the equation looks like this here: 1/2 the mass of the object times the velocity squared of that particular object. Let's do an example just to refresh our memory a little bit. How fast would a 50-kilogram ice skater be traveling if we pushed on them with 75 watts of power for 3 seconds? Okay, so we bring up power. So let's maybe start with our equation for power. So power is energy divided by time. And what I want to do is figure out, okay, if we push on somebody with 75 watts of power for 3 seconds, how much energy do we give them? So I'll take this equation and solve it for energy. And so the way this works out is when I solve for energy, it'll be power times time. So let's write this out. So 75 watts, remember a watt is a joule per second, and then we multiply this times 3 seconds. So the seconds cancel, and I'll get 225 joules. So if we push on somebody, and then with a power of 75 watts for 3 seconds, we'll give them 225 joules of energy. And so then what we do is we take our new equation, or not new equation, but the equation for kinetic energy. So K equals to 1/2 mv squared. And what are we trying to find? We're trying to find how fast. So we're trying to solve for this velocity here. And so what I'll do is I'll take this equation and write it out like this. So 1/2 mv squared equals the kinetic energy. And then I'll go through and try to solve this. So the first thing I'll do is multiply both sides by 2. So I get mv squared equals 2k. And then I'll divide both sides by the mass. So I get v squared equals to 2k divided by m. Then I'll move it over here and I'll just take the square root. So it's going to be the square root of 2 times the kinetic energy divided by the mass. And then for us, what is that? Well, the kinetic energy we gave it is 225 joules. And then the mass, we're told, is 50 kilograms. So when I figure that out myself, I got a, we'll be going 3 meters per second. So when generating electric energy from wind, we're going to use a turbine, similar to what we did with hydroelectric energy with using water, or even in some of the heat engines we've looked at using steam. And so here's a picture of a windmill slash turbine, sort of the inside of it. And again, what we're doing here is we're using a generator. So we're converting the mechanical motion, in this case rotation, into electrical current. We've looked at sort of generators before, this idea of electromagnetic induction, where through mechanical motion you can turn that into electric energy. And that's what's going on here with the wind turbine. Now with wind energy, where does this come from? Well, like a lot of the other kinds of energy we're dealing with, winds are caused by solar energy. The sun heats up certain regions more than others, and these temperature differences induce air currents or wind. Now, with wind, it's kind of difficult to talk about it because it's sort of hard to pick like one little tiny piece of wind. And so what we'll often do is think about wind in terms of density. Density, the letter for density is rho, and so we'll generally write this as rho sub air. Again, rho looks like a P. And so the density for air is 1.25 kilogram meters cubed. And so for density, what we'll call that is we'll call that the mass per volume. And so sometimes I'll write that as m times v. And so here in the book, you got this little square where it's a volume, so it's 1 meter cubed. And there's if you take 1 meter cubed of air, it's about 1.25 kilograms. And so it's how much mass would sort of be included in this little box over here. Now, what will we do with this? Well, if we need to look at the mass, what we'll do is for the masses, we'll take this equation and write it this way. The density of air times volume. Okay, so sometimes if we have an equation that deals with mass, the way we'll do that is by multiplying the density times the volume. So now to try to figure out how much energy we get from one of these turbines, let's just use our equation. So our equation is kinetic energies. That's the energy we get, again, from energy of motion. And like I said, because it's sort of hard to sort of say what piece of wind are we talking about, what we'll do is we'll use this density times the volume. And I'll actually write out volume because there's this also velocity squared term. So here is our sort of energy, the energy that we'd be talking about. 1/2 rho times the volume times v squared. And so for volume, we use this picture from the book. And this is the volume of air that hits the turbine in some period of time that we'll call delta t. And so this whole thing is the volume of air that would hit the turbine in a period of delta t. So to draw this out a little bit. And so the volume of this thing here, it's a volume of a cylinder. And so here, this would be the radius of the turbine. And so sort of the area over here would equal pi r squared. And then the height of this cylinder here is just going to be the velocity of the wind times delta t. And you can think about that, velocity has units of meters per second, time has units of seconds. They cancel to leave units of m. And so this cylinder here would have an area of pi r squared. So let's write this out. So 1/2, got that rho. And then this volume here, I'll write it as pi r squared. So that's the sort of the base of the cylinder, pi r squared, and then times the height of the cylinder, which is the v delta t. And then, of course, we've got the v squared left over. And so I can rewrite this as 1/2 the density. I'll do pi r squared. I'll combine this velocity over here to get velocity to the third power, and then write it as delta t. All right. And so, of course, we won't ever ask you to do this proof, but it's just nice, I think, to kind of walk us through it a little bit. So you have this equation here, 1/2 rho pi r squared, v squared, and delta t. And so now we're going to do this trick where I was going to say, okay, I'm just going to divide both sides by delta t. And then here, the delta t just cancels. And here we get energy over time. Well, what is that? Well, that's just our power. And so the power you can develop with one of these wind turbines, the equation looks like this right here. So it's 1/2 rho pi r squared v squared. I'm sorry, v to the third power. And there's one more thing we're going to add. We're just going to add this little guy here, which is the efficiency, which is a number that would run from 0 to 1. All right, and so we could have, in a sense, a 100% efficient turbine or 0% or somewhere in between. And we're going to find that there's actually a limit to this efficiency, which is why we're putting it in here in the first place. Okay, so here's the equation as written in the book. And so the author sort of points out, because having this go as velocity to the third is not very common. And it actually means that this thing really starts to get going at high speeds. And you can sort of see here that basically as the speed gets bigger, it's going to again be velocity cubed. And so the power is going to get bigger and bigger. And the way you can think about this is from our normal equation, right, of kinetic energy, we have 1/2 m v squared. And so there's sort of, these three powers of velocity. So two of them come from just the normal equation, 1/2 m v squared. The third comes from the fact that the wind, right, if it goes faster, more wind is going to be passing through there. And so it's like an extra piece of, term of velocity because of this. All right, and as we mentioned, the efficiency is actually limited by what's called the Betz limit. And so the maximum efficiency you can have for a wind turbine is about 59%. And if you think about it, it can't be 100% because otherwise the turbine would stop the airflow. And then what happens is all the other wind would just sort of divert around the stopped air. And so you can't get 100% efficiency. So typically the efficiencies we have are going to be between 40 and 50%. And we'll usually tell you in the problem which kind of efficiency we're dealing with. But just keep that in mind that you can't get higher than 59%. And then typically it's going to be in some range less than that. All right, so let's try a quick example. How much power could you expect a small 4-meter diameter 3-blade wind turbine situated atop of your house to deliver in a 5 meter per second breeze. And so, of course, this is of, not if. All right, so we got our nice equation. So power equals 1/2 the efficiency, density of air, pi r squared v cubed. So a couple things. So first of all, the 3-blade thing doesn't matter. That doesn't change anything. And then over here, 4 meters is the diameter, but the equation asks for the radius. Well, radius is half of the diameter. So if it's a 4-meter diameter, it's going to be a 2-meter radius. And so let's start writing this out here. How much power could you expect? So 1/2. Now the efficiency, we know it's somewhere between 40 and 50%, right? And so let's just call that 45%, sort of split the difference. Again, if we're asked a question like this, what could you expect? That's a pretty good number. The density of air, as we had talked about, is 1.25 kilogram per meters cubed. We got pi, and then again the r squared is going to be that 2 meter squared, and then the velocity. And so this is a velocity of 5 meters per second. Again, that's to the 3rd power. And that velocity is a pretty good breeze. In fact, the author goes through and shows that that pretty much is a good average breeze that kind of would work for most sort of things that we're going to do. So that'll be a real common number that we'll pull out. Okay, so when I went through and did this, I got about 440 watts. And so that would be the power that I can be delivering with that particular setup there. And before we leave the idea of these turbines, one more thing we want to talk about is there's also limits to how densely these rotors may be situated. And so the side-by-side separation, sort of kind of going this way, you want about 5 to 8 diameters of the rotor in order for that to actually, again, to be the sort of most efficient. And then the wind direction separation going the other direction this way, you want that to be of neighborhood of 7 to 15 diameters. And so actually, right now, sort of a popular way to do that is to have 8 diameters times 15 diameters. And so if we kind of just go through that real quick. So one thing that they calculate then is how much land area you're going to have in a case like this. So the area, if you do 8 diameters times 15 diameters, when you multiply those together, you get 120 diameters squared. Now remember that a diameter is just twice the radius. So we take this number 120, and then for the diameter I'm going to write in 2r squared, which gives me 120. Now 2r squared is going to be the same thing as 4 times r squared. And so 4 times 120 gives me 480 r squared. So this would be the total land area you'd get for each one of these rotors. And so let's show a picture, because that's also something that's kind of tricky to see. So these yellow lines are kind of like the rotors. And here we've spaced them out this way that people do nowadays, where it's sort of 8 diameters this way and 15 diameters this way. And what you can do is if you kind of make a little center mark in every box there, okay, what you can do is you can kind of draw this area, which is the same area. It's still going to be 8 times 15. But when you draw it this way, at least for me, it kind of makes more sense. So here's this total area of 8 times 15, and there's one turbine in that area. Here's the other area over here, and there's one turbine in that area. And you can sort of keep drawing these over and over. Here's another one. So here's this area of 8 by 15, and then there's one turbine in there. And so one thing that they talk about in the book is they talk about the fill factor. And that's basically, what's your percentage of land area covered by one of these guys. And what you can do to find the fill factors, we'll call that FF, is it's basically the area of one of the rotors, pi r squared, divided by sort of the total area that they take up, sort of the total land area that is sort of the area of each of these turbines. So you cancel out the r squared, and you get pi divided by 480. If you divide this out, you get something like 0.0065, which comes out to be 0.65% And so in this sort of standard way of doing it, where you're 8 by 15, your fill factor comes out to be 0.65, which again is the sort of area of your turbine divided by the total land area. It just gives you a sense of sort of how much area you're sort of filling up with these turbines. So what we can then do is take our equation for power, right, which was 1/2 the efficiency, the density of air, pi r squared times velocity third, and then divide by the total land area. So again, let's just use this one we've been using of 8 times 15. So we get 480 r squared. So the r squareds cancel. And so then this equation works out to be pi over 960, the efficiency, density of air, times velocity cubed. And what this is going to do is this gives us a sense of how much power we can get realistically from wind power per area, right? Which is going to be units of watts per meter squared. That we've used these units quite a bit. And if we actually use an efficiency of about 0.4, and again this sort of wind speed of 5 meters per second, this power divided by area comes out to be about 0.2 watts per meter squared. So we can use this to compare to other types of renewable energies. And in fact, we'll see that this P over A for solar, when we get to there, is something in the neighborhood of about 200 watts per meter squared. Okay, a few more things. Wind speeds do tend to vary over time. This graph here kind of shows you this. For very low speeds, the turbine may not have enough wind to turn it all, and so you can see over here there's some parts where it's basically moving very little, if at all, so maybe the wind's just not blowing enough. But also, most turbines have a max output to keep the turbine from getting damaged. And so you can see over here, it's sort of possibly that's where it reached its max output. And so what happens is, at those high speeds, the turbine will deliberately twist its blades to stop catching as much wind, to sort of slow down, and even twisting so much that it stops turning completely. So again, one of the downsides is that the wind does vary over time. So then moving on to the pros. The pros is, this is something that's replenished daily by solar illumination, so it is a renewable. Technologically, it's pretty simple, has a decent efficiency. The life cycle CO2 emission is much less than fossil fuel. It's also economically viable, right? People are putting these up, and it actually makes them money. So it's something that's a good thing. And wind is also is able to scale up to cover a meaningful fraction of the energy demand. There are some downsides, of course. Wind is intermittent. We just talked about that. Power only when nature allows. Many places don't produce enough wind. Wind can cause environmental disruptions to habitats, etc. And of course, they're kind of ugly and noisy, and so sometimes people don't like that. Finally, we can get a sense here of how much wind power we're actually using. So there's a picture of the United States with sort of a color map. You can see that Texas is a really big user of wind power. Overall, again, if you look at sort of worldwide, there's about 592 gigawatts of installed possible wind power. Right now, the average use is about 125 gigawatts, which gives us a capacity of about 21%. And so, the author goes through, and you can make a rough estimate that there's as much as 0.7 terawatts of power from wind in the U.S. So this does fall short of our total output of energy, 3.3 terawatts, but at least it is something that's substantial. And so, the author's sort of rough take on this is that, this is something that's going to be a significant contributor, but wind alone is not going to be able to replace fossil fuels much the same way that hydroelectric